Have you ever been just walking down a completely normal city street, maybe admiring a new glass building, and suddenly you get hit by this massive, almost aggressive gust of wind?
Oh, yeah, like it just came out of nowhere.
Exactly. Or, you cross an avenue into a public plaza, and suddenly the air just feels, I don't know, drastically cooler, like 10 degrees cooler than the block you were just on.
Right. And most of us just write that off as the weather being weird that day.
We do. We totally take the built environment for granted. We tend to process architecture as just this visual thing, like, is the facade pretty? Are the materials nice? But those random sensory shifts you feel, those are actually the direct output of some incredibly complex environmental dynamics interacting with human-made structures.
It's actually a fascinating collision between nature and concrete.
And understanding that collision is exactly what we're unpacking in today's deep dive. We are looking at an amazing lecture from Nuno Dias Cordizos from the Universidade de Lisboa. It was delivered on March 2nd, 2026, and it's all about environmental comfort and energy efficiency.
And really, the core premise here requires a total paradigm shift in how we even think about architecture.
Also,
Well, there's this tendency to think the design process starts the second an architect puts a pen to paper. Sketching out the spatial flow, picking out materials, focusing on the aesthetic impact.
right, the fun stuff.
Exactly. But a truly rigorous approach means the most critical phase of design happens way before any of that. It happens before a single line is drawn. It's a phase entirely dedicated to, well, analytical observation.
Which the source material refers to as step zero.
Step zero. Yes, it's the perfect name for it.
It really is. The idea is that step zero is this comprehensive, multi-layered analysis of climate data. It's decoding the atmospheric realities of a specific site, so the building doesn't just sit there fighting the elements, but actually uses them to keep people comfortable and save energy.
And we're not just talking about casually checking the local weather app to see if it rains a lot.
No, definitely not.
This is a highly formalized empirical methodology. We're looking at how urban planners take these vast meteorological data sets and translate them into physical, static structures that actually perform dynamic, thermodynamic functions for the people living inside them.
So for you listening right now, our goal today is to basically give you architectural X-ray vision.
I like that.
We're going to deconstruct this whole hierarchy of climate analysis. We'll start from these massive continental weather engines, zoom all the way down to the fluid dynamics of the street corner outside your window right now, and then look at how cities have to adapt to a rapidly changing climate.
To start that process, we really have to look at the hierarchy of climate itself, because climate isn't just one big monolithic thing.
Right, it operates on this multi-scalar continuum.
Exactly. Architects analyze environmental data across three deeply interconnected but distinct levels. You have the macroclimate, the mesoclimate, and the microclimate.
The big picture, the regional picture, and the hyperlocal picture.
Precisely. Because you really can't fully understand the localized forces acting on one single building without first understanding the massive atmospheric systems governing the whole hemisphere.
Let's start at the top then, the macroclimate. When we talk about macroclimatic conditions, we're talking about long-term, highly stabilized weather patterns, right?
Yeah, the baseline patterns that dictate the environment for vast expanses of land, entire nations, subcontinents.
And these are driven by the big, unchangeable geophysical traits of the Earth.
Right, things like latitude, which dictates the angle of the sun, continental topography, like massive mountain ranges that block atmospheric flow, and, of course, proximity to major oceans, which act as these colossal thermal regulators.
The overarching framework. And the source lecture relies heavily on a specific system to categorize this, the Köppen-Geiger classification system.
Yes, specifically referencing data sets updated between 1951 and 2000, it's a heavily empirical system.
It categorizes global climates based on historical temperature and precipitation records, and it assigns these specific multi-letter codes to every region on Earth.
And the really interesting logic behind the Köppen-Geiger system is that it's rooted in the idea that native vegetation is the ultimate expression of climate.
Oh, that makes a lot of sense.
Right, so the boundaries of these climate zones are actually defined with the limits of native plant life in mind. The first letter in the code is the major group.
So an A would be tropical climates.
Yeah.
High temps, high rain, like the equator.
Exactly. And B would be your dry or arid climates, deserts, where potential evaporation outpaces precipitation.
But the lecture focuses deliberately on the C group, warm, temperate climates.
Because that's the classification most relevant to the European context and the Mediterranean basin.
Right. And what's wild is when you look at the Cup and Geiger data for that SEAS designation, there is a massive amount of internal variance.
Huge variance. The lecture uses mainland Portugal as the primary case study to show this. Mainland Portugal is predominantly divided into two distinct classifications, CISA and CAB.
Okay, let's break those letters down for the listener because it's super important. In both CISA and CSB, the C is that warm, temperate baseline we just talked about.
Yes, and then the second letter, the ES, indicates a distinct dry season that happens specifically during the summer months.
But then they diverge on the third letter.
Right. The third letter tells you the specific temperature profile of that dry summer. So a CISA classification means a hot, dry summer.
Which in Portugal dominates the south. Regions like the Alentejo and the interior parts of the Algarve.
Exactly. Extreme summer temperatures, practically zero precipitation for months on end.
But then you have CISO. This is mostly the northern regions and the long Atlantic coastline. It still has the ES for a dry summer, but the B means the summer is just warm, not hot.
Because the Atlantic Ocean is doing a lot of heavy lifting there, the higher latitude in the north plays a small part, but it's really that continuous exposure to maritime air masses buffering the extreme heat you see further inland.
To put this in perspective, the presentation contrasts Portugal with other European seas climates. Like, let's look at the Dolomites in northern Italy.
Right. The Dolomites are classified as CIFA.
So it's still C for warm temperate, but S means it's fully humid year-round.
Yes, it doesn't have that distinct dry Iberian summer, and the A means the summers are hot.
Or we can look out into the Atlantic at the Azores.
The western and central islands of the Azores are CFB, temperate maritime, fully humid, warm summers. The annual temperature range out there is incredibly narrow.
Which means if you are an architect, building a house in the CISA heat of southern Portugal requires completely different structural and material choices than building in the CFB humidity of the Azores.
Fundamentally different. You can't just use the same blueprint.
That brings up a really fascinating point about the Iberian Peninsula as a whole. Geographically, it's sitting in this highly strategic but very volatile spot.
It really is. It's sandwiched directly between the atmospheric influence of the Mediterranean Sea and the massive unregulated expanse of the Atlantic Ocean.
Which creates a stark climatic divide. The interior, which is mostly Spain, is much more continental, arid, extreme temperatures.
But Portugal, on the western seaboard, is the peninsula's main interface with the Atlantic. The lecture actually refers to Portugal as the wetlands of the Iberian Peninsula.
I love that term, the wetlands.
Yeah.
Because its coastline just intercepts all that maritime moisture, giving it way higher baseline precipitation than Spain.
And the main engine driving that dynamic, the thing that essentially decides whether the peninsula gets normal seasons or extreme weather, is the Azores High.
The anticiclone dos Açores.
Yes. It might be the single most critical macroclimatic variable for the entire region. It's a massive, semi-permanent center of high atmospheric pressure out in the Atlantic.
And its sheer scale dictates how weather systems flow across Western Europe.
Right. When it's stable, the Azores High acts like this formidable atmospheric shield for the Iberian Peninsula.
The lecture describes it as deflecting rivers of rain.
Rivers of rain. These are highly concentrated, fast-moving bands of intense moisture traveling across the ocean.
And when the Azores High is strong and in its normal position, it literally bounces these rivers of rain northward, pushing all that heavy precipitation up toward the UK and France.
Leaving Portugal insulated from constant torrential rain, but still letting in the moderate maritime temperature.
But, and this is a massive but for urban planners, the Azores High is not a static object. It fluctuates.
It does. And if it weakens or shifts off its historical axis, that atmospheric shield essentially drops.
And when the shield drops, those rivers of rain aren't deflected anymore. They slam directly into the Iberian Peninsula.
Exactly. The presentation points to a very specific, tangible consequence of this shield failing. The severe localized flooding in Leiria in central Portugal in February 2026.
Right, which proves why macroclimatic analysis isn't just about planning for a nice sunny Tuesday. It's about understanding how vulnerable a region is to extreme events when those broader regulatory systems shift.
Which is exactly why you can't rely on macroclimate alone. A CSIC classification gives you the baseline, sure, but it completely misses the immense localized variability happening right on the ground.
Which brings us down to the second tier of the hierarchy, the mesoclimate.
The intermediate scale. Now we're zooming in from the country level down to restricted geographic zones. A river valley, a large forest, a mountain basin.
And at this scale, the big macroclimate rules get heavily modified, or sometimes just completely overridden, by local topography.
Yes. Variables like altitude, the slope's orientation to the sun, local soil thermal properties, or the presence of a lake. Those become the dominant drivers.
I think a great way to visualize this for the listener is to imagine a massive, scorching desert, a classic Köppen-Geiger B climate.
Intense heat, almost no rain.
Right. But right in the middle of that desert is a deep, naturally occurring oasis. That oasis is a mesoclimate.
Exactly. The water table and the dense vegetation create this isolated pocket of high humidity and lower temperatures that completely defies the rules of the desert surrounding it.
And the lecture highlights some amazing case studies of this in Portugal. The one that blew my mind was the Santarém anomaly.
Oh, Santarém is a brilliant illustration of topography just totally hijacking the macroclimate.
So geographically, Santarém sits in a low-lying basin. And crucially, it's shielded to the north by the Monte Junto Estrela mountain range.
And that topographical shield is the catalyst for everything. Because it's in a depression and blocked from those cooling northern winds, it traps descending hot air.
So during the summer, Santarém gets insanely hot, routinely exceeding the broader regional averages. It's just this intense pocket of heat.
But, and here's the key, it is not a dry heat, which is what you would expect in a CISA or CISA's macroclimate.
Right, because it's located directly within the Tagus River Basin.
Yes, so that geographic bowl traps the hot air, but it also traps massive amounts of moisture evaporating off the river.
You end up with an isolated zone of extreme heat paired with exceptionally high humidity.
And the practical outcome of this, Santarém supports a massive local rice industry.
Which is wild. Rice is an agricultural product you associate with highly humid, tropical, climates or monsoon regions. The fact that they grow it in a country famous for its dry summers is entirely due to exploiting that specific mesoclimatic anomaly.
It's a perfect example, and you see these mesoclimatic divides dictating conditions everywhere. Look at the Algarve.
Right, the southern coast. The whole thing shares a Kisa macroclimate.
But the mesoclimatic conditions are completely split. You have the windward side, the western part,
which gets a much more direct, unfiltered maritime influence from the Atlantic. So higher humidity, more moderate temperature peaks, more rain.
And then you contrast that with the leeward side, the eastern portion closer to Spain. It is significantly drier, has higher peak temperatures, and way more intense solar radiation.
So if a developer is planning a huge resort, the passive cooling strategies they need for the western coast are totally different from the eastern coast, even though they are in the exact same macroclimatic zone.
Absolutely. The presentation also brings up the island of Madeira as this extreme example of how mountains influence the mesoclimate, the orographic effect.
Madeira has a subtropical oceanic climate, but its topography is dominated by a central mountain range that runs perpendicular to the prevailing trade winds.
Right. So as these moisture-laden trade winds hit the northern side of the island, condenses significant precipitation on those northern slopes,
making the north of Madeira highly humid, heavily forested, and wet. But by the time those air masses cross the peaks and descend onto the southern slopes,
they've been completely stripped of their moisture. The descending air warms up and creates a significantly drier, sunnier mesoclimate in the south.
Two wildly divergent environmental realities on one relatively small island, all dictated by topography.
Which brings us to the final tier. The one that is immediately actionable for the architect, the microclimate.
We've gone from the continent down to the valley, and now we are looking at the hyperlocal conditions, the specific site, maybe a few square kilometers, or honestly just the perimeter of a single building lot.
This is where human intervention becomes a primary driver of weather. At this level, you have to map the influence of two categories, natural elements and man-made elements.
The natural elements are pretty intuitive. The specific trees on the lot, small creek, how the local topsoil absorbs heat.
But in contemporary urban environments, it's the man-made elements that almost always dominate the microclimate. Built boundaries.
Built boundaries. So the height and density of the surrounding buildings, the layout of the street grid, and critically, the waterproofed surfaces.
Yes, the immense expanses of concrete sidewalks, asphalt roadways, paved plazas, all the things that define modern cities.
And how those built boundaries interact with the wind and sun creates localized thermodynamic phenomena that architects absolutely must anticipate. The presentation uses Avenida de Roma in Lisbon as a textbook example of this.
It's a great example of unintended microclimatic engineering.
So Avenida de Roma is this prominent, heavily trafficked avenue. It's got a long, uninterrupted linear layout oriented directly on a north-south axis, and it's flanked by relatively tall, uniform buildings.
And when the prevailing winds, which are driven by the broader mesoclimate, hit that specific urban geometry, the street essentially captures the air mass.
Because the air can't easily flow through or over the tall buildings, it gets funneled directly down the avenue.
Structural confinement. It forces the air to accelerate, creating a pronounced canyon effect.
Meaning the wind velocities at pedestrian level on Avenida de Roma can be significantly higher and much more turbulent than the wind speeds just a couple of blocks away in a neighborhood with a different layout.
The urban layout inadvertently transformed the avenue into a localized wind tunnel.
Right. And if you are an urban planner trying to design a nice outdoor seating area for cafes along that street, and you fail to execute your step zero analysis, you are literally placing pedestrians directly into an engineered wind corridor. Their coffee is going to blow right off the table.
Exactly. Which segues perfectly into the core objective of Step Zero. Translating all of this massive hierarchical climate data into actionable design that ensures human thermal comfort.
Because at the end of the day, a building's primary utility, before we even talk about aesthetics or cultural significance, is to serve as a biological shelter.
To do that efficiently, without just plugging in a massive air conditioner, we have to understand the physiological metrics of comfort.
And the science of thermal comfort is way more precise than just looking at a thermometer. The lecture breaks it down into a few distinct parameters: air temperature, relative humidity, air velocity or wind speed, solar radiation, and mean radiant temperature.
Mean radiant temperature is one that people often misunderstand, but it is critical. It doesn't measure the temperature of the air itself. It measures the uniform temperature of all the surrounding surfaces that are radiating heat toward you.
Okay, so give me an example of that in a city.
Think about standing in a public square. You're surrounded by dark asphalt and brick walls. Those materials have been absorbing solar radiation all day long.
Right, they're baking in the sun.
Exactly. So even if the ambient air around you is relatively cool, those surfaces are actively radiating thermal energy right onto your skin. It drastically elevates your perceived temperature.
Because our bodies are just constant thermodynamic engines. We're trying to maintain a core temp of roughly 37 degrees Celsius, and we are perpetually exchanging heat with our environment to keep that balance.
And the environment is always pushing back. The presentation really emphasizes the parameter of air velocity, the science of wind chill, to show how environmental forces accelerate that heat exchange.
Let's talk about wind chill because it's fascinating. Under calm conditions, our bodies naturally radiate heat, right? And that warms up a microscopic layer of air resting right against our skin.
Yes, a boundary layer. It acts like natural biological insulation, but when you introduce moving air, wind velocity, that dynamic changes entirely through forced convection.
Moving air physically strips away that invisible protective layer of warm air.
It rips it right away and replaces it with ambient unheated air. So your body expends energy to heat up this new layer.
And the wind just immediately sweeps it away again.
Exactly. In cold climates, this forced convection exponentially accelerates the rate of heat transfer away from your body. The physiological consequences are immediate. Your core temperature drops, hypothermia risk spikes.
And it also accelerates evaporation, right?
Yes, the continuous airflow evaporates moisture from your skin faster, raising the risk of dehydration even in freezing temperatures. That combination of convective heat loss and evaporative cooling tricks your sensory system into feeling significantly colder than the objective dry bulb temperature.
It's incredible how vulnerable our physiology really is, which dictates that architects have to have highly sophisticated tools to balance all these variables. They can't just guess how a building will handle the site's temperature, humidity, and wind.
No, guessing leads to miserable buildings. The foundational analytical tool for this, as detailed in the lecture, is the Givoni psychrometric chart.
Oh, the Givoni chart, developed by Baruch Givoni in 1992.
It is an absolutely indispensable framework for bioclimatic architecture.
I mean, at first glance, if you look it up, it is this dense, highly complex, slightly intimidating matrix of data points and curved lines.
It can look overwhelming. The horizontal axis plots the dry bulb temperature, and the vertical axis plots the absolute moisture content of the air. And then sweeping across the whole graph are these curved lines representing relative humidity.
But the absolute genius of the chart is how it synthesizes all that intimidating data to actually prescribe architectural solutions.
Right in the center of the chart is a defined polygon. That is the comfort zone.
The sweet spot.
Yes. If the macro and microclimatic data points of your site plot naturally inside that polygon, it means a human being wearing normal light clothing, resting in the shade, will achieve thermal equilibrium without any structural intervention or mechanical climate control.
The weather is just perfectly comfortable on its own.
Right.
But the reality is most global sites experience huge chunks of the year where the data falls way outside that central polygon.
And that is where the true utility of the Givoni chart comes in. The peripheral zones surrounding that comfort area correspond to specific passive design strategies.
It's essentially a cheat sheet for the architect. If your site's data plots into one of these outer zones, the chart empirically tells you exactly which architectural interventions you need to pull the indoor environment back into the comfort polygon without turning on an HVAC system.
Exactly. Let's say your site's data plots far to the right of the comfort zone during the day. High temperatures, relatively low humidity. The chart directs the architect toward the thermal mass cooling zone.
Thermal mass, so that informs the actual materials of the structure.
It mandates that the building envelope needs to use high-density materials with substantial thermal mass. Think thick concrete, rammed earth, heavy masonry.
Because those heavy materials have the capacity to slowly absorb that intense daytime heat. They soak it up like a sponge, delaying the transfer of that heat into the building's interior.
Precisely. And then, as night falls and the outside ambient temperatures drop, that thermal mass slowly releases the stored heat back outside, regulating the internal temperature perfectly across the 24-hour cycle.
But if your data plot's in a zone characterized by high heat and high humidity, thermal mass alone won't save you.
No, it becomes ineffective. In that case, the Givoni chart points you toward natural ventilation.
So the design shifts completely. Now it's focused on cross-ventilation, placing windows perfectly to catch the prevailing microclimatic winds and creating interior layouts that let the breeze sweep through the whole house.
Maximizing evaporative cooling directly on the occupant's skin.
And conversely, if you're plotting to the left of the comfort zone sustained cold periods, the chart highlights passive solar heating and internal heat gains.
Right, so you maximize south-facing glazing to capture the sun's radiation, use super-insulated envelopes to trap the heat, and design spaces to capture the latent heat generated by the people and appliances inside.
The Givoni chart really is the ultimate expression of step zero, diagnosing the atmospheric problem and prescribing a structural, passive solution.
But the challenge of passive design is getting increasingly complicated because our building sites aren't sitting in isolated, pristine environments anymore.
No, they are plugged into massive, densely populated urban grids. And as the global population urbanizes, this concentration of man-made elements is fundamentally altering the microclimate on a citywide scale.
Which brings us to the urban heat island effect, or UHI. The lecture dedicates a lot of focus to this because it is one of the most critical threats to urban thermal comfort right now.
And the mechanics of the UHI effect are directly tied to what we just talked about, materials and geometry. Cities are essentially overwhelming concentrations of artificial waterproofed surfaces, dark asphalt, concrete, steel.
And those materials fundamentally alter the energy balance of the entire site. First off, they have a lower albedo than natural landscapes, meaning they reflect less solar radiation and absorb a lot more of it.
And secondly, just like the thermal mass strategy on the Givoni chart, all that concrete and asphalt acts like a colossal thermal battery. Throughout the day, it absorbs staggering amounts of solar energy.
Think about a rural environment for a second. The porous soil and the vegetation don't absorb as much heat, and the process of evapotranspiration from the plants actively cools the air. Plus, when the sun goes down, the rural landscape radiates its stored heat back into the atmosphere pretty quickly.
But in the dense urban core, that trapped heat is released incredibly slowly.
Because the geometry of all those tall buildings restricts the sky view factor, the thermal radiation physically can't escape efficiently into the upper atmosphere.
It just bounces around between the buildings. Consequently, the urban center stays drastically hotter than the surrounding countryside, especially at night. The city literally loses its capacity to reset thermally.
And this thermodynamic reality places urban planners in a really tough ideological debate regarding compact cities.
Right, because on paper, from a sustainability perspective, compact, dense cities are incredibly desirable.
They optimize resource distribution, they make public transit viable, they reduce the carbon footprint of commuting, and they stop urban sprawl from destroying natural ecosystems.
But the paradox is that this exact density is what causes the UHI effect. By packing all those structures, the pavement and all that human activity so tightly together, we amplify the thermal mass, We block the natural ventilation corridors, and we concentrate all the heat generated by cars and air conditioners.
Subjecting the population to severe urban stress, noise pollution, and trapped air pollution. So the architectural mandate is finding that equilibrium. How do we keep the efficiency of a compact city while mitigating the localized environmental nightmare it creates?
The source material frames the solution around principles of healthy living integration. Mitigating UHI requires really deliberate systemic interventions right at the step zero phase. It means rejecting the purely concrete landscape and fully integrating green and blue infrastructure.
And viewing vegetation not just as pretty landscaping, but as vital urban cooling infrastructure. Trees provide crucial shading, which lowers the mean radiant temperature of the asphalt below them, and their evapotranspiration actively drops the ambient air temperature.
Cortizos also heavily emphasizes the sociological necessity of what he calls social design. Sustainable urban architecture has to facilitate human interaction. It has to blur the rigid lines between private interiors and public exteriors.
Creating outdoor living rooms, public plazas that are thermally comfortable, shaded pedestrian corridors, integrated parks.
Because when public spaces are actually designed to mitigate environmental stress, they become these amazing hubs for community engagement, tolerance, cultural exchange. But if a public square is just a hostile, sweltering concrete wind tunnel,
Yeah.
people abandon it. It breeds isolation.
Exactly. And when we look for historical precedents of successful microclimate-aware urban integration, we actually don't need to look at speculative sci-fi cities. The presentation highlights a profound historical example right there in Lisbon.
The Baixa Pombalina. This is such a staggering example of using urban morphology to engineer a healthier microclimate.
It really is. And to appreciate it, you have to remember the context of its creation. After the catastrophic 1755 earthquake, the tsunami, and the fires, the medieval center of Lisbon was virtually obliterated.
Total destruction. But the reconstruction, led by the Marquis of Pombal, presented this incredibly rare opportunity to entirely reimagine the urban grid from a blank slate.
Right, and instead of rebuilding the labyrinthine, winding, organic street patterns typical of medieval Europe, the planners instituted a highly rational orthogonal grid system.
But the true genius wasn't just making it a neat grid. It was the specific alignment of that grid. The primary avenues were oriented on a strict north-south axis.
A deliberate microclimatic intervention. The planners observed that the prevailing dominant winds affecting Lisbon originate from the north.
So by aligning these wide, unobstructed avenues directly with that dominant wind vector, they essentially designed a massive city-scale ventilation system.
The presentation uses the Portuguese term varar, which means to sweep.
To sweep, I love that. The north-south corridors allow the prevailing winds to seamlessly penetrate the dense urban core, sweeping out the stagnant air, the trapped heat, and the heavy air pollution of the 18th century.
The grid continuously directs this flow downward toward the Tagus River. It is a brilliant, entirely passive solution to urban ventilation and thermal regulation. And it was executed centuries before anyone formalized the Giovoni chart or ran computational fluid dynamics models.
It just proves that step zero analysis, observing the dominant environmental forces and shaping the architecture to harness them, has always been the hallmark of enduring design.
It has. However, there is a massive caveat. The Baixa Pombalina was designed for the macroclimate of the 18th century.
Right.
The most pressing challenge facing contemporary architecture today is that our environmental baseline is no longer stable.
Which brings us to the future outlook of the discipline. We absolutely cannot discuss environmental comfort without confronting the reality of a rapidly shifting climate. Those macroclimatic categories we talked about at the beginning, the boundaries of the Quises Mises B zones, they are geographically migrating.
The lecture cites projections from the Intergovernmental Panel on Climate Change, the IPCC, and the picture for the European continent is stark.
The trend points unequivocally toward hotter, significantly drier summer seasons, coupled with winters characterized by more intense, concentrated precipitation events. The extremes are just widening.
And for urban environments that are already struggling with the heat island effect, this shifting baseline triggers a highly dangerous, self-reinforcing thermodynamic feedback loop.
The AC Dune loop. As baseline summer temperatures rise, the UHI effect amplifies. The thermal mass of the city absorbs unprecedented levels of heat, making urban centers increasingly uninhabitable during peak periods.
And the immediate reflexive human response to being uncomfortably hot is the mass deployment of active mechanical cooling systems, air conditioning.
But air conditioning is a thermodynamic trap. An AC unit does not magically eliminate heat. It simply transfers it.
Exactly. To lower the temperature inside your apartment, the system consumes vast amounts of electrical energy to extract thermal energy from your living room and physically vent it outside into the street.
So as the city gets hotter, millions of AC units work harder. They simultaneously draw massive loads from the power grid and pump immense volumes of anthropogenic waste heat directly into those narrow urban corridors,
Which further elevates the microclimatic temperature of the street.
which intensifies the UHI effect, which causes the ambient temperature of the buildings to rise, forcing the AC units to consume even more energy and expel even more heat. It is just this continuous escalating cycle of energy consumption and urban heating.
And breaking this doom loop is the absolute imperative of modern architecture. We cannot mechanically cool our way out of a shifting climate. The physics simply do not allow it.
So what's the path forward?
The only viable path is a radical recommitment to step zero analysis and passive design principles. The goal has to be designing building envelopes that are so highly optimized for their specific microclimate that their inherent demand for mechanical cooling drops to near zero.
But the presentation does highlight a crucial opportunity here, especially for regions like Portugal. The shifting climate brings immense stress, yes, but it also provides a staggering abundance of raw, renewable energy.
The data shows Portugal is positioned as one of the sunniest nations in Europe, receiving between 2,300 and 3,200 hours of solar insolation every single year.
So the future of architectural energy efficiency relies on shifting from a model of energy consumption to localized energy generation. We have to move beyond viewing solar panels as these clunky modular accessories bolted onto a roof.
The discipline has to fully embrace building integrated photovoltaics, BIPV. The solar harvesting technology needs to be seamlessly incorporated into the facade, the glazing, the actual roofing materials.
The architecture itself must become the power plant, using the intense solar radiation of those Kiza and Keys-B climates to offset whatever minimal energy demand remains after all the passive strategies are exhausted.
And crucially, achieving this level of performance requires accepting that there is no universal architectural solution anymore.
Right. A hyper-efficient, sustainable design perfectly calibrated for the microclimate of Lisbon is going to fail if you build it in Berlin. Or, honestly, even in another region of Portugal. True sustainability demands an absolute rejection of the copy-paste architectural methodology.
The lecture utilizes the Portuguese island territories to definitively prove this point. The insular environments demand incredibly bespoke structural responses. Let's look at the Azores one more time.
Okay, the Cive maritime climate.
Building there, subjected to the persistent multi-directional forces of the Azores High, is an entirely different discipline than building on the mainland. The architectural priority in the Azores is not mitigating extreme heat, it is managing pervasive, highly corrosive moisture.
It requires advanced dehumidification strategies, hyper-resilient waterproofing, and structural designs capable of withstanding continuous, high-velocity wind loads from multiple vectors.
Now contrast that with the island of Madeira, where the mesoclimate is fractured by that central mountain range. An architect cannot simply design a Madeira house.
Because the north and south are completely different, they have to design a northern slope Madeira house, which requires strategies to handle high humidity, constant orographic precipitation, and lower solar exposure.
Or they must design a southern slope Madeira house, which demands shading, thermal mass, and ventilation to manage a much drier, high sunlight environment. The microclimatic data of the exact site has to dictate every single material, structural, and orientational decision.
That right there is the ultimate thesis of Step Zero. Architecture is not the imposition of a preconceived form onto a landscape. It is the physical manifestation of deep, rigorous environmental listening.
It requires understanding the global meteorological engines, mapping the regional topographical deviations, analyzing the fluid dynamics of the urban street, and deploying passive thermodynamic strategies to align the built environment with the biological needs of the human body.
We've covered immense ground today, tracing the invisible forces that shape our thermal reality from the shifting mechanics of the Azores High all the way down to the molecular boundary layer of air resting against your skin.
We've seen how topographical bowls like Santarém create unexpected agricultural miracles, and how the geometry of Avenida de Roma creates unintended wind tunnels.
We've explored how tools like the Givoni chart offer a literal blueprint for passive survival, and how the Marquis of Pombal utilized the north winds to sweep 18th century Lisbon clean.
And we have outlined the daunting parameters of the future, the necessity of breaking the mechanical cooling feedback loop, integrating renewable generation into the very fabric of our buildings, and the absolute requirement for highly localized, site-specific design in the face of a warming continent.
As we wrap up this deep dive, I want to leave you with a final, complex challenge to consider. Throughout this whole discussion, we've focused heavily on the future, on how architects must utilize step zero analysis to design new structures capable of withstanding the shifting climatic baseline. But look closely at the city around you right now. Consider the cathedrals, the historic civic centers, the centuries-old masonry blocks that define our cultural heritage.
Those structures are entirely static. They are massive, immobile, thermodynamic machines that were designed and calibrated for a specific macroclimate that existed hundreds of years ago.
But the baseline is moving. The Köppen-Geiger maps are shifting. As the summers grow drastically hotter and the urban heat island effect intensifies, the passive strategies embedded in that historical architecture will inevitably begin to fail. They were not engineered for the thermal loads of the mid-21st century.
No, they weren't.
So the monumental question for the next generation of urban planners is this: how do we retrofit our architectural past to survive our climatic future? How do we implement the rigorous demands of Step Zero on priceless, immutable heritage sites without erasing the very history we're trying to preserve?
It's an incredible challenge. A climate is rewriting the rules of the environment, and our existing cities must find a way to adapt.
Thank you for joining us on this deep dive. Next time you walk through your neighborhood, take a moment to observe the invisible thermal landscape shaping your experience. Keep questioning the environment around you.